So now that we understand a little bit about what absolute and local maximums and minimums actually are, we need to start talking about how can we determine where they are going to be located on a function if we don't have a picture of the function. What if we were only working with a function formula? How would we know where these spots are going to be? And so to help with that question, let's take a look here at example 3. Now here we're going to take a look at this function of f of x we already looked at in this section, and we want to determine something very specific related to the derivative of this function at specific points. So let's take a look here at part A together. I'm interested in the derivative of my function f at the value of 4. So remember, when we hear the word derivative, what we have to think immediately is slope of a tangent line. So what we're curious about here is that if I was to go to the x value of 4, go to the function, and think about the tangent line that I would construct here, I'm curious, what would the slope of this line likely be? Well, since it's a flat line, we would probably state that f prime of 4 is equal to 0. The slope of that line would be 0. Now, what about if I went to go ahead and take a look at f prime of negative 1? Well, what I'll see here is that at this point, notice I have a corner point, a sharp corner. And at a sharp corner, there's kind of like, I guess, a couple different tangent lines we could draw. Since the tangent line has to move again in the same direction as the curve, if we were moving this way along our function f, we would see that we would get a tangent line looking like this. But if we were drawing tangent lines after coming up out of this parabola sort of shape, we might get a tangent line that looks like this. And so what we see is that I don't really have a tangent line to work with. Remember that at a corner point, a function is not differentiable. So we can say that f prime of negative 1 is undefined, right? There is no value there. We can't compute this. This isn't possible. So it's undefined. You could say it does not exist. You could say that, something like that, right? I can't find a slope of a tangent line there. So this is kind of a really interesting observation. Notice that at these particular points, when x is a 4 and I'm up at 4 comma 5, or when x is a 1 and I'm at negative 1 comma 2, these points here are both local maximums. And you'll notice that if I was to look at the spots where local minimums occur in this picture, I could see that again I would get a tangent line here with a slope of 0, and a tangent line down here that is not going to exist. So I can see a really, really interesting idea that these mins and maxes appear to be occurring at the points when my tangent line slopes are 0 or when they are undefined. And this is summarized in what we call Fermat's theorem. Here's what it says. If a function has a local minimum or maximum at a value of c, at an x value, and if the derivative exists at that value, that is, if I know that there's a local min or a max somewhere, and my derivative doesn't come back undefined or does not exist, then automatically we must have a tangent line of slope 0. So this is kind of a really interesting thing. So as I state down here in the note, Fermat's theorem implies that there is a horizontal tangent at points that correspond to mins and maxes of the graph, at least when it's differentiable, when I can actually draw a tangent line there. So this is really interesting. When there are horizontal tangent lines, or when there are mins and maxes, there are always going to be horizontal tangent lines there if the derivative exists. So we'll see a little bit more about how we can make use of this interesting fact as we continue to look at examples in this section.